In this video, we're going to finish up our look at reversible nucleophilic addition reactions by focusing on imines and enamines. An aldehyde or a ketone can react with a primary amine to form a hemiaminal, which will then lose water to form an imine. Keep in mind, a primary amine, that doesn't tell you about the structure of the alkyl group, that tells you about how many alkyl groups are connected to the nitrogen. So this is a primary amine, and the final product is an imine. So we've seen some examples of imines before when we talked about a Friedel-Crafts acylation followed by a Wolff-Kishner reduction. Here we actually go through the formation of an imine, and then this goes through a few more steps, eventually leading to CH2, CH3. So the result is that this carbonyl is reduced all the way down to a CH2 group. In lab last week, you treated an unknown compound with phenylhydrazine. You actually used 2,4-dinitro phenylhydrazine, but notice this is a primary amine, and so when this reacted with an aldehyde, it would form an imine where we have the carbon-nitrogen double bond. So many of these compounds can be used as derivatives of an unknown. Then you can get the melting point of the derivative to identify the derivative, and once you identify the derivative, you can figure out what your original compound was. And one more important example of imine formation involves this compound, retinal, which reacts with a protein called opsin, and there's a particular amine residue, and this will combine here to form this imine that is called rhodopsin with the double bond N, and so this is connected to the protein, so this complex is called rhodopsin. So this complex is responsible for fission because this will undergo cis-trans isomerization at this particular alkene that leads to a signal that's transmitted to the brain that leads to fission. So this is probably the best example that shows the importance of imine formation. So when we look at the overall reaction, we have an aldehyde or a ketone reacting with a primary amine to form first a hemiaminal. This one is analogous to formation of a hydrate, formation of a cyanohydrin, and then this will lose water. In particular, it loses an OH and an H from adjacent atoms to form the carbon-nitrogen double bond imine. But how does this work? So we can think about it as the amine acts as a nucleophile, shares its electrons with the carbonyl carbon, pushes these electrons up onto the oxygen, giving us this intermediate. Now, this isn't against the rules, as we mentioned earlier about having an O- and an N+. That's not against the rules like having an O- and an O+ at the same time. But still, it doesn't look very good, right? So alternatively, it might be more reasonable to think about carrying out this reaction under slightly acidic conditions. So careful control of the pH is important because you want it to be acidic enough so that this can be protonated, which is going to make this first step more reasonable. But if it's too acidic, then this nitrogen is going to get protonated, and then it can no longer act as a nucleophile. So whether you think about proton transfer before nucleophilic addition or nucleophilic addition followed by a couple of proton transfers, it looks something like this. So from here, this can grab off a proton, put these electrons here. This can grab off a proton, put these electrons here, and that gives us the hemiaminal. Now the OH can grab a proton, pushing those electrons back onto the oxygen, giving us this protonated species. Water can leave. This should look familiar. This part is very similar to what we saw with acetal formation. Once water leaves, we get this carbocation, and this is stabilized by resonance because we have another resonance structure we can draw that looks like this. But now here's where it diverges from what happens with an acetal, because rather than something acting as a nucleophile, instead we can have water, for example, act as a base, pull off that proton from the nitrogen, push these electrons onto this bond, forming a double bond between the carbon and the nitrogen, giving us the imine. Now, in our last example, we have enamine formation. So in this case, we're looking at an aldehyde or a ketone reacting with a secondary amine. And as an intermediate, we get this hemiaminal. And then from here, we lose water. But notice there's no hydrogen on the nitrogen, so we can't lose OH and H. We can't lose OH and H from the same atom, but instead we're going to lose OH and H from the neighboring carbon. So we're going to lose water from here and here, giving us the enamine. An enamine has an alkene and an amine. So how does this work? Again, this could be similar to what we just saw with the imine, where if the reaction is carried out slightly acidic, then this might get protonated first, and then the amine can add, pushing these electrons onto the oxygen, so that would give us this right away. And then water can grab off this proton, put these electrons onto the nitrogen, giving us the hemiaminal. Now the OH can grab off a proton, putting these electrons back onto the oxygen, giving us this protonated species. I forgot to mention this on the previous slide. Keep in mind, if the OH grabs a proton, we're going to move forward. If the nitrogen grabs a proton, then we're going backwards. And so these are all equilibrium steps. And so there will be forward and back, forward, forward, back, back. All of that is going to be happening. So just be aware of that. So we're up to this species, and then water can leave, giving us this carbocation, which again is stabilized by resonance. But now water can grab off this proton, allowing these electrons to fold in here to form the double bond, giving us the enamine. Just like I mentioned for imine formation, with enamine formation, pH control is important. We want it to be acidic enough to protonate the carbonyl so that this is a really good electrophile. But if it's too acidic, then this nitrogen gets protonated and then it cannot act as a nucleophile at all. So keep in mind the similarities as well as the differences between reactions of primary and secondary amines with aldehydes and ketones. So finally, let's pull it all together and look at a bunch of different examples. So starting with this aldehyde, let's come over here. If we treat this with potassium cyanide, then the cyanide acts as the nucleophile and shares its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, giving us as an intermediate this, and then reaction with HCl, this oxygen is going to grab off a proton, giving us OH, HCN. So we form a cyanohydrin. If this aldehyde is reacted with this primary amine, we are going to get, as an intermediate, this, and then this will react further with the loss of water. We're going to lose the OH from here and the H from a neighboring atom. If the nitrogen has a hydrogen, then this is where we're going to lose the hydrogen. So we lose H, OH to give this compound. So remember, this piece came from the aldehyde, and this used to be the carbonyl carbon. Now it is the imine carbon. In this example, we are treating the aldehyde with a secondary amine. So we are going to get something that looks like this. Here is our nitrogen connected to an ethyl group, connected to another ethyl group. Now this is going to lose water. We can lose the OH from this carbon, but there's no hydrogen over here, so it has to lose a hydrogen from over here. So that will give us this, probably as a mixture of cis and trans. And notice in this case, this is what used to be the carbonyl carbon. And then last example, if we have an aldehyde and we treat it with a diol in the presence of an acid. So paratoluene sulfonic acid or tosic acid, this is a commonly used acid just because it is relatively easy to work with. It's a solid, so that makes it a lot easier to work with than some other acids. So this gives us a cyclic acetal. So as we're looking at the different types of nucleophilic addition reactions, it's important to think about the common features as well as the differences that distinguish one type of reaction from another.